Hi, hello friends. Am I audible? Welcome back to Electrical Machines Quick Revisions. You please let me know in the comment box. Am I audible? Just drop your message in the comment box. Can you guys hear me? Why there is no response from your side? Okay, I hope you all can hear me. So let us start the revision from where we left. In the last session, we have been completed the basics of the alternator, and I have been discussed about the some important factors. We have been discussed about the EMF equations, principle, Fleming right-hand rule, how to apply Fleming right-hand rule and the left-hand rule. And in generator, we are using Fleming right-hand rule. In motor, we are using Fleming left-hand rule. Then we have been seen the classification of the armature winding. Then we saw the factors, winding factor, under winding factor. We have been discussed about pitch factor, under distribution factor, and we saw the relation between coil span, poles pitch, and in short pitch what will happen, in full pitch what will happen. At last, we also concluded that in alternator and motor, how armature reaction is playing a vital role. If your motor is in unity power factor, what type of magnetizations will be predominant inside the machine. Suppose if we are taking alternator, it is working at a 0.8 lagging power factor. We also seen that under that point factor specifically, how our alternator are practically predominantly, what type of armature reaction has been predominantly occupied in our machine. We have been seen all those things. So let us start from where we left in the last class. I have also given some quick revision. What quick revision I had given, like the relation between power factor and magnetization effect we saw. What we saw, if we are taking power factor is inversely proportional to magnetization effect or demagnetization effect. These both people are going to be inversely proportional to our power factor. This relation we saw. And I also told you that if you are taking voltage regulation into the if you are considering voltage regulation, then voltage regulation also will be inversely proportional to the value of power factor. So these things we were concluded in the last class. Now let us discuss about the types of the rotors that we are using. And I'm just quickly coming to that point. What are all the advantages and disadvantages are there over the types of the class, that is classification of the alternator. We know basically we are having two types of rotor in our alternator. We will be having two types of rotor in our alternator. What are those? One is cylindrical rotor, one is cylindrical rotor, and the second one is salient pole rotor. So we will be having two types of rotor structure. One is cylindrical, another one is salient pole. Now cylindrical means what? If you are observing this cylindrical machine, your rotor will be simply a solid cylinder, that's all. When we are considering salient pole machine, salient means on the rotor periphery you can observe that poles will be projected in the outward. Poles are projected in the outward like this. And here also you can observe, I am not drawing this properly, just adjust, yes. So if you are observing the rotor structure like this, then that is called simply what? Salient pole machine. That is the basic difference between cylindrical and a salient pole machine. So this is the structure of rotor for cylindrical, this is the structure of rotor for salient pole machine. After that, we will be going to cover stator. Here we are going to place the stator on the top of the rotor by keeping a sufficient amount of air gap. Now when we are talking about the cylindrical rotor, field winding will be placed on the rotor, yes we all know. Armature winding will be placed on the stator, yes we all know. Same case everywhere, even in other type also. In salient pole also field winding will be placed on the rotor and armature winding will be placed on the stator. What is the main point that we must keep it in our mind is, Field winding is distributed and all the coils are connected in series. So here the type of the field winding is distributed. The type of the field winding is distributed one and all of its coils are connected in series. So all the coils of the field windings are connected in series. That is the basic nature of the field winding. And one more thing is between stator and rotor you can observe the air gap. The air gap is minimum. When I am comparing this air gap with a salient pole machine, cylindrical pole machine is having very less amount of air gap. So air gap is minimum in case of cylindrical rotor type synchronous machine when I am comparing it with the salient pole machine. At the same time, when I am talking about cylindrical rotor, it can be operated at a high speed. It can be operated at a very high speed. That can be possible when I am talking about cylindrical motor. The first point I told, field coil is distributed and all the coils of the field are connected in series. And second kind, I told you that between stator and rotor we will have minimum amount of air gap. And the third one is it can be operated at a high speed. So that's why it is called high speed alternator, or some people are calling it as turbo generator. It can be called high speed alternator. We are calling it as high speed alternator, and we can also call it as turbo generator. Turbo generator. So it will be operated at a very high speed. That is the another point notable. And the next thing is, if you are observing the diameter of the cylindrical rotor, this diameter of the cylindrical rotor is very less. Diameter of the cylindrical rotor, diameter is small, you can say diameter is less. At the same time, axial length will be high. Sir, what you are trying to mean here? Let me tell you. Axial length means, so your stator is having like this. See there, this is the basic side view of this rotor structure. So if I am observing this, this is the front view, cross sectional view. So here this diameter is very less, whereas this axial length is very high, such that it can be operated at a very high speed. So these are all the some of the advantages that we have to keep it in our mind when we are thinking about cylindrical type of synchronous machine. Suppose if I am designing the salient pole machine, then what are all the concerns that we have to keep it in our mind? Let us take the salient pole machine. So when I am talking about salient pole machine, in case of salient pole machine, just now I have been shown the structure. If you are observing the rotor of the salient pole machine, poles are projected in the outward periphery. See there, this is the structure of the rotor. And you can observe, you can keep as many numbers as possible, number of poles, it depends on the application. But the thing is here, the salient pole winding are concentrated. First one, in case of salient pole machine, winding is concentrated. Salient pole machine, in salient pole machine, the winding is concentrated. The winding is concentrated in nature, concentrated winding, and as usual they are connected in series. I'm talking about the salient pole field coil rotor. And the next thing is, we know in salient pole machine we are having two axes. One is called direct axis and another one is called quadrature axis, that is q axis. One is called a direct axis, another one is called quadrature axis. And the phase angle difference between the direct axis and the quadrature axis is always 90°. It means they are always perpendicular to each other. And the next thing is, if you are observing the air gap in case of salient pole machine, sometimes it is minimum, sometimes it is maximum. What I am trying to mean is, if you are taking direct axis and a quadrature axis, the air gap is minimum between direct axis. If I am taking direct axis and stator, if you are observing the air gap between direct axis sorry guys, if you are observing the air gap between the direct axis and stator, air gap will become minimum. I can say the air gap will be minimum. We can say air gap is minimum. If you are observing the quadrature axis, then I can say between the quadrature axis and stator you will be having maximum air gap. So what I can say is, here your air gap will become maximum. So just remember these points, because it is quick revision class. Here I cannot explain everything on step by step. I'm just trying to give as all the points, like key points. You have to just write it in a short manner and then try to solve as many problems as possible. Definitely it will be helping you to crack all theoretical questions and problematic numerical questions. So let us continue with this. Now already we saw that when I was discussing about cylindrical type of machine, we saw that the speed is very high because its diameter is very small and its axial length is very high. So this is suitable for high speed. When we are looking into the salient pole machine, the diameter is large. So here I am talking about the diameter of the salient pole machine. So it is having large diameter. You can observe the structure. Its diameter is very large, its structure is very big, so diameter is very large and axial length is very small. Axial length is very small. So axial length is very small, so this one is suitable for low speed application. So this alternator will be suitable for low speed application. Which one it is? This is salient pole machine. I have clearly explained it. Salient pole machine is suitable for low speed application. I hope you all understood. So that's why it is simply called. It is called hydro alternator. So we are calling it as hydro alternator. Hydro alternator. It is also called hydro alternator. What about the previous one? Cylindrical machine. That is called turbo alternator. I hope you understood what I would like to mean here. Now, let us keep our attention with the voltage equation. Now, when we are taking our machine, synchronous machine, from the vector diagram, I am not bringing the vector diagram here. I am just quickly revising all the concept. From the vector diagram, the internally developed voltage and alternator can be easily calculated with the help of E is equal to square root of V cos pi plus voltage drop across the armature resistance plus IARA whole square plus here it is become V sin pi plus or minus IA into synchronous reactance XS whole square. This is the expression for developed voltage and alternator. We can also call this voltage is no load voltage, or the total voltage that will be developed inside the alternator. Yes sir. Here if you observe, I have put two signs here. One is plus and another one is minus. Why we are keeping these two signs here? What is the purpose? They are actually talking about the under the power factor, in which power factor our alternator being operated. Suppose if your alternator is being operated at a lagging power factor, if we are operating our alternator at a lagging power factor, then I can say here you have to use plus. Suppose if you are operating the alternator at a leading power factor, then in the formula you must keep minus. So leading power factor. And here I hope you all know this V stands for per phase voltage. V stands for per phase voltage. It will be given per phase terminal voltage, that will be given, and IA, that is per phase armature current. Per phase armature current. And pi stands for external power factor, that will be given. Cos pi is external power factor or external power factor angle, we can call it as. Pi stands for power factor angle. Now after observing all these parameters, you can easily calculate the other values. See, RA means what? Armature resistance drop per phase. XS means synchronous reactance per phase. So all the parameters are per phase parameter. So the voltage that you are calculating here, that is also per phase voltage. Got it? I hope you understood. And in the same fashion, let us continue the lecture. Okay, this is how we are calculating the voltage expression, and that too, this is for alternator. I told I am writing this expression for alternator. Suppose if we are talking about the motor, this is synchronous alternator. Let me write down the expression for synchronous motor. 1 minute. Yes. So here, let us take the motor. Suppose if I am talking about synchronous motor, then what can be the expected expression for the voltage, induced voltage calculation? So this voltage can be written as, once again, square root of, this is motor, right? So we have to reverse the operation. It means Here you will be getting V cos pi minus Ia into Ra whole square. Then in the second part, here it will become plus V into sin pi. As usual, we are going to keep plus or minus Ia into Xs whole square. Now here also we know once again this is per phase voltage, this is power factor angle, armature resistor, synchronous reactance, armature current. Everything is clear. Again I put plus or minus sign. Now in case of motor, it is very important to keep the observation. If I am putting plus sign, if your motor is being operated at the leading power factor, then positive sign will be appearing here. So this plus sign will become sorry, we have to put plus when your motor is being operated at a leading power factor. You have to put minus when your motor will be operated at a lagging power factor. Got it? So after that, immediately now we understood how to calculate the voltage expressions at all. After knowing this, what is our next target is we have to express the voltage regulation. What is the formula to calculate the value of voltage regulation? We must explore the value of voltage regulation. Let us have the quick revision. What is the formula to express the value of voltage regulation? It can be simply written as E minus V by V into 100. This is the formula to calculate the voltage regulation. Actually, it is the ratio of the change in terminal voltage to the rated voltage. That's all. Yes. So this is the generalized formula in percentage. I wrote this formula. Next, you might have studied that there are few more formula we will be using. In case of voltage regulation, we will be having zero voltage regulation and we will be having maximum voltage regulation. And we should remember the formula to calculate the zero voltage regulation and the maximum voltage regulation. Can anyone please let me know what is the formula for minimum voltage regulation? When I am talking about, when I am saying that the voltage regulation is minimum, then what is the condition for minimum voltage regulation? Minimum voltage regulation means we can call it as zero voltage regulation. For zero voltage regulation, I am just asking you to write down the condition. So when I am talking about zero voltage regulation, first one is in case of alternator, what is the formula for zero voltage regulation? Condition, just to remember the condition. Basically in our alternator, when I am talking about zero voltage regulation, we will be considering cos of theta plus phi, that is most important formula, will be equal to minus armature current Ia into Zs, synchronous impedance Zs, divided by twice of voltage V, that is per phase voltage, supply voltage. Okay, per phase supply voltage you can put it here. And armature current, synchronous impedance, everything is fine. Now what about this theta and what about this pi? So let us talk about theta and pi. If I am taking theta, it will be simply talking about impedance angle. Theta will be simply talking about impedance angle, whereas phi is dealing with the power factor angle. It means what? Impedance angle means when we are talking about the alternator, we will be having some synchronous impedance. Now take into that consideration, taking this value synchronous impedance further can be written as armature resistance Ra plus J times of synchronous reactance. From this, you can explore the value of theta by putting tan inverse of imaginary xs divided by Ra. This will be helping you to calculate the value of theta. Whereas pi stands with the power factor angle. Power factor angle means what? Amount of voltage, nature of the voltage that you are connecting. Based on the nature of the voltage, between your current and voltage, you will be having a certain phase angle. That is called power factor angle. So you must keep your attention with that power factor angle. So for your understanding, let me quickly draw the phasor diagram. See, if I am taking nature of the load is lagging. If I am taking nature of the load is lagging, then for alternator, the phasor diagram can be simply drawn. I am talking, see, in alternator we know E is equal to supply voltage V plus Ia into Zs. That is the simple form of bringing the relation between voltage and that is external voltage and internal voltage. E stands for induced voltage. This is per phase voltage plus armature current Ia. In detail, it can be written as Ia at an angle of pi, that is power factor angle. This sign signature will change based on the nature of the power factor angle that will be given. If they are talking about lagging power factor, then you must put minus pi. If they are talking about leading power factor, then you have to put plus pi. Because in case of leading power factor, current will take a lead. current will be in advance. So for leading power factor you must keep plus pi, for lagging power factor you have to keep minus pi here, do remember. So ia at an angle of pi and synchronous impedance zs at an angle of theta. So this is how we are bringing the relation between induced voltage and other parameters. Now in rectangular domain, it can be written as per phase voltage, terminal voltage into armature current IA. Simply I can write armature resistance RA plus J times of synchronous impedance XS. Now if you are expanding this further, I can say per phase voltage plus armature current IA into RA plus J times of armature current IA into synchronous reactance XS. Now how will you represent it in power factor? Sorry, in phasor diagram. In phasor diagram, I have to start from voltage, that is terminal per phase voltage, and I have also told you that I am assuming that the nature of the load is lagging one, and I also told you this is practical case. In practical case your current is always lagging in nature, so this will become your armature current, and the phase angle difference between the terminal voltage and armature current will be considered as pi, that is power factor angle pi. After that, if I am adding armature resistive drop will be added with the per phase voltage like this. This line should be in parallel with the armature current. So I can say this will be your armature resistive drop. After that, if I am drawing a perpendicular line to this armature current extent, I am just extending and I am drawing a perpendicular line to this, and that will be talking about armature, that is synchronous reactance drop. If you are adding all these things to put together, you will be facing the value of E, induced voltage. Now if you are deeply observing, the phase angle difference between E and the armature current I is simply called power factor angle psi. If I am defining the angle between the induced voltage and the armature current, that is called internal power factor angle. Psi means internal power factor angle. It is the phase angle difference between the induced voltage and the armature current flowing into the synchronous machine. Meanwhile, I have also defined one more power factor angle, that is external power factor angle. It will be vary, it depends on the nature of the load. This is the phase angle difference. This power factor angle defined between the per phase output voltage and the armature current. Meanwhile, we have to talk about one more person, that is called delta. So this delta is called power angle or load angle. So this it will be belongs to, that is here we are defining the delta between induced voltage E and terminal voltage E V, terminal voltage V. So between E and V, whatever the phase angle that we are defining, that is simply called delta. So just remember these three parameter, because here you have to bring the relation. If you are observing the phasor diagram, see there armature current IA is here. I'm just drawing for your purpose understanding. This is per phase voltage, and somewhere we are having E here. So the phase angle difference between V and E is delta. Phase angle difference between V and IA is pi. Then the phase angle difference between E and IA will become psi. From this I can say the internal power factor angle will be the sum of delta plus pi. So this case will be true whenever alternator is being operated at a lagging power factor, and this case is a true for alternator. So just to remember this relation, this is how you have to bring. Don't memorize this formula first of all. Suppose if your alternator is acting, it is working under leading power factor, then draw the phasor, again try to bring the relation. In the same fashion, you can also write down this relation for motor. Okay. Now let us enter into the another task. I told you that from the phasor I brought all these things. So this is impedance angle, or we can call external power factor. Sorry, this is impedance angle. We are talking it as synchronous impedance, and phi is dealing with the power factor angle. We saw apart from this psi, that is called internal power factor angle, delta, that is called load angle. So totally here I have been talking about four angles. One is synchronous impedance is alone offering some angle, that is called theta, whereas terminal voltage and armature current is offering some angle, that is called pi. And then induced voltage and armature current is offering some angle, that is called psi. Between induced voltage and terminal voltage we have some angle, that is called load angle delta. Understood? So you have to keep the relations between all these parameters. Now let me bring the next one. The another one is I have been discussed about voltage regulation, and I told you that we are talking about here. I wrote the condition for minimum, that is zero voltage regulation. This is the formula to explore the value of minimum, that is zero voltage regulation. After that, immediately once you understand this, I am asking you, is there any other relation? Yes, So under this situation, when we are observing that your alternator is approaching to zero voltage regulation, then I can say the value of theta plus pi almost will become equal to the value of 90 degree. We can say the value of theta plus pi will become equal to 90 degree. Both these conditions are true here. So either you can derive in this way, but this is the formula. This is the one that will be often using in the examination for zero voltage regulation calculation. I hope you all understood what I am trying to mean it here. Next, let me write down the condition for maximum voltage regulation. Write down. Let us discuss about maximum voltage regulation. Condition for maximum voltage regulation. Condition for maximum voltage regulation. So when I am talking about maximum voltage regulation condition, you might be observed the impedance angle will become equal to power factor angle. That is the condition for maximum voltage, or I can say this is what impedance angle or internal angle, this will be equal to power factor angle. This is the condition for maximum voltage regulation. You know what is theta, you also know what is pi. Just now I have derived both of them clearly one by one. Okay. Now let us enter into the characteristics of the alternator. Now you understood what I am trying to mean by voltage regulation. Yes. So what you have to remember is, wait, before defining characteristics, I would like to give some more points also. So when we are observing the voltage regulation in the alternator, it will be useful for you. From the voltage regulation curve of the alternator, what I can say is the voltage regulation is always positive, not everywhere. I'm just giving the conclusion. This voltage regulation is always positive when we are connecting the purely resistive load. Purely resistive load. These are all the sum of the observation. If the connected load is purely resistive, then the nature of the voltage regulation is always positive. Connecting the resistive load means I am connecting unity power factor load. Am I right? That is called unity power factor load. And the next thing is, if they are giving that the load of the alternator is highly leading power factor. If it is highly leading power factor, then also you have to consider your alternator should be positive. Voltage regulation of the alternator will become positive when the another key given that the alternator is operated at a high leading power factor. High leading power factor. And this value voltage regulation will become 1 minute. So the voltage regulation will become, see here I made a small mistake. This is for highly lagging power factor. We have to draw the voltage regulation curve. So if I am drawing the power factor versus voltage regulation, you can observe that this curve is going like this. So here this zone is lagging power factor zone. My tongue is flipped, forgive me. That is lagging power factor load. This zone is leading power factor zone. So here there is a chance, see there, this whole zone is leading power factor zone. Here only we will be having the chances to face zero regulation, and here only we will be having the chances to face negative voltage regulation. This is the value of voltage regulation. Y axis is basically talking about voltage regulation. X axis is dealing with the power factor. So power factor, when power factor will become lagging, voltage regulation will be positive. And if they are saying that lagging power factor is very high, then there is a highly chances it is always be positive. So when I am talking about, if they are saying that voltage regulation is zero or voltage regulation is negative, that cases are possible only when your alternator will be operated at a leading power factor. Sorry for the confusion, just to correct it. So the voltage regulation will become positive when it is purely resistive load, and also when it is highly lagging power factor, and it will become zero. Yes, it will be zero. And what is the other possibility? It can be zero, and it can also be negative. It can also be, or it can also be negative. When it will become negative, there is a chances when it is being operated at a leading power factor. And remember, at a leading power factor you will also having some positive values. If your leading power factor value is very, if it is very close to 1, if it is very close to 1, another situation what I can say, the value of the the value of the voltage regulation will become positive. See there, the graph is going like this. So it is having positive value, zero value, negative value. All the chances are there in the lead at the leading power factor. So if they are saying that leading power factor is more, if they are drooping into this line minus 0.8, minus 0.7, when the value of leading power factor will become more and more negative, then I can say obviously the voltage regulation will become positive, sorry, negative. Voltage regulation will become negative, and we also have the chances to face the zero voltage regulation. So zero voltage regulation will be occur only at the leading power factor. That condition is very important and you must keep it in your mind. Now, let us discuss about characteristics of the alternator. I am just drawing the waveforms. You have to remember this because sometimes these characteristics will be directly given in the examination and you will be requested to identify the type of the alternator, that is characteristics. The first one we are going to discuss about obviously open circuit characteristics. Open circuit characteristics. Open circuit characteristics, so let us take two terminal, one is x-axis, another one is y-axis. So here we will be dealing with, in case of open circuit, we will be dealing with the induced voltage E versus field current IF. Yes. So under this situation, when we are talking about, when we are drawing the open circuit characteristics, the one more most important point is speed should be kept it as constant. Speed of the alternator is constant. We are driving the alternator at a constant speed and we are drawing the curve between induced voltage and the armature current. So when you are field current, when I am continuously increasing the value of field current, your voltage of the alternator will be slowly build up, increasing. After that it will be reaching its maximum value, then it will get saturated. Clear? So this is called open circuit characteristics of the alternator. Similarly, if I am talking about short circuit characteristics, then what will happen? Let us see. Let me draw the short circuit characteristics of the alternator. The next one is short circuit characteristics. I am just quickly revising everything. Uh, I am not going detailing. I am just giving the points that are required in short. So this is short circuit current versus field current. If you observe the short circuit current versus field current, you will be getting the linear line. So the short circuit characteristics of the alternator is always linear. Remember that. Whereas the open circuit characteristics of the alternator is non-linear. Open circuit characteristics of the alternator is almost non-linear. These are all the 2 points that you have to remember from here. And what is that saturation point? This is the point where we will be obtaining the rated voltage. If you are trying to operate the alternator beyond this, what will happen? Alternator will get saturated. There is no use of increasing the current further. So what I can say is, yes, 1 second. This is the maximum induced voltage. It has been developed here. Got it? Yes. Next, what we are going to discuss about here is we have to talk about load character. One by one, I'm bringing here. Let me do one thing. I will be completing ZPFC first. What is the expansion of abbreviation of ZPFC? Zero power factor characteristics. If you want to write down, you can write zero power factor characteristics. We are going to discuss about zero power factor characteristics of the alternator. What is the relation? Once again, zero power factor characteristics has been drawn between the terminal voltage versus field current. Whereas we have been observed that open circuit characteristics we have drawn between induced voltage, internal voltage versus field current. Whereas here, zero power factor characteristics we are developing between terminal voltage versus field current. And here you have to remember few more things. The point. First, your speed should be kept it as constant. We are going to maintain the value of speed should be kept it as constant. And in the name itself, I am suggesting that this is called zero power factor characteristics. So what is the value of power factor? If you are observing the value of the power factor will be assumed to be zero power factor lagging. It is purely lagging. We are assuming that it is purely lagging in nature. Okay, that is what we are trying to keep it as the assumption. And one more thing, what we are going to maintain constant here is armature current. IA also will become constant. So when we are developing zero power factor characteristics, the points that you have to remember is it should be drawn between terminal voltage versus field current. During this testing, during this characteristics testing, armature current should be kept it as constant, speed of the machine should be kept it as constant, power factor being operated, that is alternator will be operated at a zero power factor lagging. So it is purely zero power factor lagging. Now if you observe the characteristics curve between voltage versus field current, then it will be started somewhat here. This is most important. You can observe this question once asked in your examination also, this characteristics. So this is called zero power factor characteristics of alternator ZP Okay. Now let us keep our attention with the external load characteristics. Next most important point is external load characteristics of an alternator. When we are talking about external load characteristics, let me draw the external load characteristics. If we build the external load characteristics, first of all, it will be drawn between terminal voltage versus what? Armature current. They are the external parameter. Since I am calling it as external load characteristics, we have to consider external parameter alone. So here the external parameters are your terminal voltage and armature current. As usual, the things that we are going to keep constant here is first one, what? Speed of the machine should be maintained as constant. First one. And second thing is armature current also going to be maintained as constant. See, sorry, not armature current. See, this is somehow I'll be doing these chilly mistakes. But it is big one. You should remember this. Field current will become constant, not armature current, because we are going to develop the curve between VT versus IA only. So field current should become constant, and one more most important term will become constant here. That is power factor also should be maintained as constant. So when we are talking about the external load characteristics of the alternator, there are three parameters which are should be permanently maintained as constant during this characteristics observation. One is speed, another one is field current, another one is power factor. Don't forget, they are very important. Now let us build the characteristics, that is external characteristics of the alternator. If you observe, it has been drawn between armature current versus voltage V, as I told you that. So initially it will be started at E. V will become equal to E. E and V both are equal when the armature current is 0. After that, what will happen is they have to form a straight line, but due to the practical characteristics of the alternator, it will not follow a straight line. When I am continuously trying to increase the value of armature current based on the nature of the regulation and power factor, these characteristics will get drooped. So how these characteristics are going to get drooped? First thing, if your alternator is being operated at a zero regulation, if it is given that your alternator is being operated at a zero regulation, then in under that situation, what I can say is this E is permanently maintained. There is no any drop in the machine. So this is talking about, this straight line is talking about zero regulation curve. First conclusion. Now I will be bringing some other worst parameter and good parameter one by one. Suppose if I am operating the alternator at a unity power factor, if the nature of the load will be connected as unity power factor, then you can observe there is a small drooping. Yes, definitely drooping will be there. Then your characteristics curve will be like this. So this one will be talking about unity power factor. So I will be just giving the name here and I am just interlinking. One will be talking about unity power factor. And suppose if our alternator is being operated at not unity power factor, a slightly 0.8 lagging power factor, then your curve will be again drooping. Second one, this will be talking about 0.8, I can say practically, that is 0.8 lagging power factor. Still, if you are trying to down the power factor to less than log, see, we are going towards lagging, more and more lagging. I have started the unity power factor. We are observing only drop and the resistive and the reactance drop. After that, if you are trying to operate the alternator at a lagging power factor, then again your curve will droop. Again, if I am still decreasing it some 0.5 or 0.6, again it will get decreased. Again further, if you are bringing it to zero power factor lagging, then it will be again further will be decreasing. This is for zero power factor lagging means what? Power factor will become zero. So alternator, that is your load will become purely inductive. There is no resistor. Now let us repeat the case in the above characteristics. See, I am talking, I have started at a unity power factor, then I have started putting more and more lagging load. Then when I am observing the waveform, that is characteristics, it was continuously drooping down, drooping down. So now what I am going to do is, suppose if I am trying to operate the alternator at a leading power factor, then what will happen? Let us see the cases. If you are operating the alternator at a 0.8 leading, then you can observe the curve will become slowly somewhat like this. Okay, so this will be for 0.8 leading power factor. Still, if you are trying to increase the power factor, suppose if I am trying to operate the alternator to 0.6 leading, then it will become like this. So this will be talking about 0.6 leading. I am just considering the practical constraints. If you are still trying to operate it at 0 power factor leading, then it will become somewhere here, that is 0 power factor leading. Okay, now what is the conclusion? At a leading power factor, when your alternator will be trying to operate it, if you are trying to force your alternator to operate it at a leading power factor, you can observe that the terminal voltage, see, this is the terminal voltage. I am drawing this curve for terminal voltages at all leading power factor. Whatever the graph that we have observed here, it is clearly indicated that the terminal voltage will become higher than the value of internally induced voltage. Yes or no? You might be observed this type of observation in our transmission line also. When the receiving end voltage will become, sometimes your receiving end voltage will become higher than the value of sending end voltage. Sometimes it will become less than the value of sending end voltage. Like that, even in your alternator also, when it will be operated at a leading power factor, your terminal voltage will become higher than the value of induced voltage. So some theoretical questions will be formed. When your alternator output voltage, terminal voltage will become higher than the value of induced voltage. It can be possible only at a leading power factor. Understood? Yes. So this is the complete external characteristics of the alternator. I hope you all understood how to do this. Now let us talk about one more person, that is called load saturation characteristics. This is most important. This type of questions are being asked in your examination. I am taking this from your examination only. See the examination. In the examination they have asked this type of questions. From that we can, I'm showing that when your load is being saturated, that is called load saturation characteristics. Here what we are going to do is, we are trying to draw the curve between terminal voltage versus field current, that is called load saturation characteristics. So when I am bringing this, as usual, there are few more people are going to be constant. One is, first, your speed of the alternator should be maintained as constant, and second one is, power factor of the alternator should be maintained as constant, and third one is, we kept two things. One is speed and field power factor, and field current is varying. Obviously we are going to maintain the value of armature current is constant. So three parameters are constant here. One is power factor, armature current, another one is speed. Do remember whatever the terms that I am projecting here, because in your examination point of view you can't expect any type of questions. Questions may be framed in different ways, right? You know that. So let us draw the characteristics, that is load saturation characteristics. Let us see how it will be. We are going to draw the curve between voltage versus current only. I am calling it as field current. Now what will happen here is, initially it will be started somewhere here. See, what people will do is, we are calling it as load saturation characteristics. So after a certain ampere of current, right, when you are continuously increasing the value of field current, voltage will be developed, and after a certain point it will be reaching saturation point. After that, further what will happen, that is what I am going to do now. So load saturation curve, basically it depends on the type of the load. If you are operating the alternator at a unity power factor, then the nature of the characteristics will be like this. This is for unity power factor, and as usual, if I am trying to droop, if it is lagging, then it will become 0.8 lagging. Then again, if you are increasing, putting more lagging load, then it will become 0.6. Sir, I am not bringing any proof how it happened, because it is revision class. I cannot explain everything. I told that I will be bringing everything which are required, because we are revising, we are not explaining from the beginning. So just to note it down directly. If you are having any doubts, you can also go back and you can watch our lecture. It is available in our playlist. Okay. Now see that this is unity power factor. Suppose if I am putting leading power factor, then it will become 0.8 leading. Yes. Then again, if you are putting 0.6, then it will become somewhere here. If you are putting 0 power factor, then it will be somewhat here. Yes. So this is for 0.6 leading, and this is for 0 power factor lead. Got it? So this is the load saturation characteristics. It has been drawn between terminal voltage versus field current. Now the most important point we are going to discuss, that is called compound characteristics of the alternator. Let us discuss about compounding characteristics. This is called compounding characteristics of the alternator. Sir, what we are doing here in compounding characteristics, what are the parameters should be we have to consider? So when I am talking about compounding characteristics, it will be drawn between field current versus armature current. First conclusion, when we are developing these compounding characteristics, speed should be maintained as constant, first parameter. And voltage, terminal voltage also should be maintained as constant. And the third one is power factor also going to be maintained as constant. Understood? Yes. Now if you draw the curve, between armature current IA versus field current IF, this characteristics curve, usually field current having certain amount of value. See, let me start from here. So this will be the starting point. After that, once again based on the nature of the load, if you are operating the alternator at a unity power factor load, then the drooping characteristics will be going somewhat like this. So this is for unity power factor. Further, if I am operating it at a lagging power factor, then it will be going like this. 0.8 lagging you can consider. If I am putting more lagging power factor load, it will become point. This characteristics will be like this for 0.6 lagging. Again, if I am putting 0 power factor lagging, then it will be going like this. So this will be for 0 power factor lagging. After that, if I am talking about leading power factor, then how I will draw it? If I am talking about leading power factor, this is how it will be. This will be for 0.8 leading power factor. Suppose if I am reducing, if I am putting more leading, that is 0.6 leading, then it will become like this. If I am putting 0 power factor leading, then somewhat like this. This will become 0 power factor leading. I hope I have been discussed all types of, that is all characteristics which are very important in your examination point of view, and you might have got the conclusions. So for whatever the things that you haven't observed properly, now kindly note it down and try to revise it as many times as possible. Then while solving the problem, you can apply all these things together. Definitely it will be helping you to bring the answer. Okay, yes. So after that, what we have to discuss here is short circuit ratio. From the characteristics of the alternator, immediately after completing this, we'll be talking about a person that is called SCR. It is simply called SCR. Is not silicon controlled rectifier here. We are in electrical machines. Here it is called short circuit ratio. This is called short circuit ratio. So when I am talking about the short circuit ratio, how can we define this short circuit ratio? What is the standard formula? There are so many ways we can define the short circuit ratio. One is you can consider the field current, that is field current demanded by the alternator to achieve the rated open circuit voltage versus, that is field current, that is the required field current to achieve the rated open circuit voltage, divided by field current demanded by the alternator to achieve the rated short circuit current. So this will become rated short circuit current. So this will be short circuit current, this will be rated open circuit voltage. Now if you take the ratio between the field current demanded by the alternator to produce the open circuit rated open circuit voltage divided by field current demanded by the alternator to produce the rated short circuit current, that will be directly giving you the value of SCR, short circuit ratio. What is the alternative way? Instead of focusing on the values of the field current, suppose if you are having the value of short circuit current divided by open circuit voltage, sorry, 1 minute, let me define. In terms of per unit also we can define. I am defining it in that way. First of all, if you are having the short circuit current and base current, actual rated base current, if you are taking these two, then you can define in terms of, that is simply nothing but short circuit current in per unit. See that here I am putting actual short circuit current. In the denominator, rated current means it will be talking about the base current. So short circuit ratio can also be explored in terms of short circuit per unit value. So if the short circuit current is defined in per unit value, directly you can take that value, that will become equal to the value of short circuit ratio. And it can also be alternatively defined in terms of synchronous reactance. That is, synchronous reactance means short circuit current versus open circuit voltage only. From this, what I can say, this can be further written as open circuit voltage divided by short circuit current. So here I am neglecting the value of, here I am neglecting the value of armature resistance. I am assuming it approximately equal to 0, and I am considering only open circuit voltage and short circuit current. And with the help of these two quantities, you can define it in per unit. So it is inversely proportional to synchronous reactance, that too saturated synchronous reactance. Remember, because we are taking the saturation point only. So that is saturated synchronous reactance, and we are defining it in per unit. So we will be going up with the per unit values to define this quantity. Okay, so here whatever the parameter that you are considering, that is in per unit. By using this, you can calculate the value of synchronous reactance at that is synchronous reactance you can calculate. After that, by taking the reciprocal for the synchronous reactance, you can explore the value of short circuit ratio. So this short circuit ratio can be explored in many ways. This is way number 1, this is way number 2, and this will become way number 3. Okay, sir. Now let us see some of the observation that you must keep it in your mind while talking about the short circuit ratio. Points to remember from the short circuit ratio. What are all the points? We have been talking about two types of rotor. I hope you all remember. One is cylindrical rotor, and another one is salient pole rotor. So based on the cylindrical pole rotor, it will be acting as a, this rotor type machine is called turbo alternator. I have given some name for this. Yes, if our rotor structure is designed with the help of, if you are designing the rotor by using cylindrical structure, then that alternator can work as a, it can be operated at a very high speed. That's why we are calling it as turbo alternator. Yes, we are calling it as turbo alternator. Similarly, if I am talking about salient pole machine, we are calling it as hydro alternator. Just now I have discussed. We are calling it as hydro alternator. Now, when we are talking about turbo alternator and hydro alternator, in case of hydro alternator, the value of the short circuit ratio is very high. Quite a bit, it is high. When I am talking about the turbo alternator, the value of the short circuit ratio is low. Remember these points, they are very important. Okay. Now, the next question is, what is the relation between voltage regulation versus short circuit ratio? That is, the question is, if I am having more short circuit ratio, it means whether we are having better voltage regulation or poor voltage regulation. That is the question. So in a synchronous machine, whenever you are observing that the value of short circuit ratio is very high, if the value of short circuit ratio is very high, it means it is having better voltage regulation. You can say that it will be having better voltage regulation. It is having better voltage regulation. I am just concluding from the observations. So it is having better voltage regulation. And one more thing is, if the short circuit ratio is very high, comments about the steady state stability. Steady state stability of the alternator. What is this steady state stability? In power system, there is one separate chapter is called stability analysis of the alternator. When sudden fault or suddenly some unexpected malfunctioning are happening in the power system, because of that your alternator power generation will get disturbed. So it may leads to acceleration or deacceleration, but alternator will not be remains stable for few minutes. During that period, your alternator will be continuously sustained between some acceleration and deacceleration point. Then it will be coming back to slowly settle down to new steady state point. So steady state means basically it is talking about stability of the alternator. When sudden jerk will be happen, sudden fault will be happening, sudden malfunctioning, sudden short circuit in the power system. Because of this, there is some disturbance. During the disturbance, how your alternator is successfully damping out all these issues. That is basically talking about steady state stability. If your alternator short circuit ratio is very high, then your alternator steady state stability is, it will be having a better improvement in the steady state stability. So what is the conclusion? More short circuit ratio leads to improvement in the steady state stability limits. We can call it as better value is, it will be having improvement in the steady state stability limits, such that it will become more and more stronger against of faults or sudden changes. Okay. Next thing is sorry guys, sorry for the inconvenience. Okay. Let us continue. Suppose if your machine is having a low value of SCR, it means the stability of the machine will be what? Less. So you have to, it is vice versa. If the short circuit ratio is high, I can say the system will become more and more having, it will be having improved stability limit. If the value of the SCR is low, it means stability of the system will become less. Okay, I hope you understood. That's all. So these are only some of the observation that we have been observed from the what? Short circuit ratio of the alternator. Yes, I hope you all understood these things. Yes. And the next thing is, for this short circuit ratio, we will be having some limits. Let me tell you limits. If you are talking about short circuit ratio, suppose if I am taking salient pole machine, that is a range, practical range. So in case of salient pole machine, short circuit ratio is lies between 0.9 to 1.5. This is for salient pole machine, SCR range. Suppose if I am talking about cylindrical machine, then the short circuit ratio lies in between 0.6 to 0.9. Suppose if I am talking about some synchronous condenser, if I am talking about synchronous condenser, whereas the value of short circuit ratio SCR will be bounded between, no, actually it is very less, let me approximately equal, range is not required for synchronous condenser. Let me put, so this value of short circuit ratio will become across approximately equal to 0.4. That's all, understand? And apart from that, let me give few more notes or tips to remember. There are few more observations from the short circuit ratio. Let me give. The question is, what is the relation between voltage regulation versus short circuit ratio? Sir, just now we saw, if the short circuit ratio is more, then we will be having better voltage regulation. What is the meaning of better voltage regulation? Basically, voltage regulation is talking about the amount of the voltage that is being dropped in our alternator between induced voltage and terminal voltage. We will be having resistor and synchronous reactance. How much amount of voltage will be getting dropped here? So if the drop is more, if the voltage drop is more, then the voltage regulation is poor. The relation voltage drop and voltage regulation are inversely proportional. What I am saying is, when the drop is more, it means if you are having more voltage drop, it is poor value. No, you should not allow your alternator to drop more voltages. If it is dropping very less amount of voltage, then the maximum amount of generator voltage will be, you can receive it across the terminal voltage. So when the voltage drop is more, voltage regulation will be poor. If the voltage drop is less, then the voltage regulation will be super, that is better. So better voltage regulation means, basically in terms of value, if we are talking, better voltage regulation means value of the voltage regulation is very less. Value means suppose the drop in percentage, if I am saying only 1% voltage drop, 2% voltage drop, 0.5% voltage drop, then percentage wise it is having very less amount of voltage drop. Out of, suppose if your alternator is generating some 10,000 voltage, out of this 10,000 voltage, only 1% means what will happen? 1% of 10,000 will become 100 voltage will be dropped, remaining 9,900 voltage you can receive at the output terminal. So this is better voltage regulation, because in percentage wise the voltage regulation value is very less. So voltage regulation value is less and we are calling it as super better voltage regulation. So short circuit ratio is increasing in the sense better voltage regulation. In terms of value, I have to define SCR is inversely proportional to the value of the voltage regulation, such that when we are having more short circuit ratio, you will be having very less value of voltage regulation. If the value of the voltage regulation is very less, it means we are having better voltage regulation. Percentage wise, very less amount of voltage will get dropped inside the alternator. That is the point that you should keep it in your mind. Another point is, people will be talking about the relation between short circuit ratio versus armature reaction. So they are always inversely proportional. If the armature reaction will be continuously increasing, then it may leads to decrease the value of SCR. So they are inversely proportional to each other. And the most important point, let me bring, this short circuit ratio is directly proportional to the cost of the machine. It is depends on, if you are investing more cost, based on the availability. If I'm investing more in cost on the machine, such that short circuit ratio also will be improving. So whenever you are trying to increase the value of SCR, it means you are investing more cost on the alternator. So cost and SCR are directly proportional, and it is also directly proportional to size of the machine. That is what I'm saying. When we are investing more cost, size of the alternator will get increased. If the size of the alternator is increasing, obviously short circuit ratio also can be increased, and it is also directly proportional to air gap length. That is most important point, air gap length. The question is, if we are increasing the short circuit ratio, it means what is the air gap length, or the relation will be vice versa. When the air gap, if you are observing more air gap between the stator and rotor, then short circuit ratio will be very high. And we also seen that short circuit ratio is directly proportional to stability of the machine. So if you are increasing more SCR, your steady state stability limit will be improved. It means system stability will be improved. And if I am increasing the excitation, what happened to the SCR? Definitely SCR value will get increased. Understood? So next thing is, suppose if I am increasing the value of synchronizing power, then also SCR will increase. And if I am increasing the value of output power, then also SCR will increase. So these are all the some of the relations that we are directly having between the SCR and other parameter. See, I hope these sessions are really most useful for every one of you. So I'm trusting you all. You will be giving your support for us. I am trying to reach entire Tamil Nadu people, at least to give your best support, such that they will be receiving highly qualitative content for their examination. It's not like you can study everywhere, you can do whatever the blah blah things that you want, and you can directly going the exam. If you are going like this, the track should not be maintained its consistency. It may leads to less result. You will not expect that, you cannot expect that productivity 100% efficiency. That's why most of you are after spending huge amount of money, or after investing huge amount of time for the studies, without proper way of studies, without observing the proper content from the sources where you are taking, you people are losing your scores. So it doesn't matter how much amount of duration that you are investing for the studies. All about is how the way you are preparing, whether you are going up with the exact content that are required, or you are learning something which are not important. First main agenda is exam. Once you get the very good score, then you can keep your attention with the other parameters. Like if you want to do some research, yes, you can do. First create some backup, join in some good sectors, after that you can do. So please do subscribe and click that bell icon, because I am coming live as soon as every day. I'm trying to come in live, and I'm trying to deliver as much content as possible. So definitely it will be supporting you all for your examination. At the same time, you will be learning the way to prepare the short notes for all other subjects also. For that I need your support. Try to share it with all your friends, and click that like button if you are really getting some good information from our channel. Okay, so this is all for this lecture. In the next